Okay, so we'll be getting started. Today I plan on finishing functions and also going over complex numbers. So as I talked about before, a function is basically a machine that allows for outputs to have multiple inputs, but not the other way. So each input has to have an output, only one output, and these outputs don't have to be unique. And we designate this fx or any letter you want, any variable you want, really. And so we call what someone can input into this the domain. So for most part, the domain is all real numbers. 2x minus 3 equals fx. Domain is all real numbers. However, for something like fx equals 1x, x cannot be 0. So the domain would be all real numbers except 0. Similarly, anything that can be generated by the function is called the range. So this is the input is according to what x could be, out is what fx can be. So for example, so absolute value, which is these double marks, can only be non-negatives. So the square root, non-negative. So it's anything that can be generated by the function. Okay, so function combination. I'll be moving a bit quicker today, so just stop me if anything's unclear. So I skipped a slide. So function combination. So let's say we have xx times gx. So the input here is x into both of these functions. So what we can do is just substitute whatever fx is and gx is. So if x is 1x and gx is x squared, then 1x times x squared. However, there's a pitfall here. If we were to simplify this would be x. However, f cannot have an input of 0. Its domain does not allow that, which is not reflected in this answer. So you need to watch out for domain issues when combining functions. It would be similar if, say, this were a divide. This would be 1 over x3, which is actually, that's a bad example, since it keeps the x can't be 0. If you had plus 0, never mind, that's also a bad example. Well, anything that's combined with fx can't have the input of 0. So when you combine functions, if we say this is hx, then the domain of hx would be real numbers minus anything that's excluded, or anything that's excluded from these two functions. You could also see it as the intersection of these two domains. Any number that is shared between these two domains. So this is OL numbers, this is OL numbers minus 0, so it's OL numbers minus 0. When I talk about intersection, you see these Venn diagrams. This would be the intersection, 1, 2. The middle part's the intersection. On the other hand, for the domain, it's X. However, the input can't be 0. So it can't, the hx, as we just named it, can't be 0 either. So the range would be whole real numbers, which is R minus 0, which would actually be done like this if you wanted to write it formally. This 3 lines symbol, parentheses, negative infinity, 0 parentheses, which is meaning that it can't be 0 or negative infinity, and which is this. No, it's this. That's a better drawing. And 0 infinity, it can't be 0 on this side either. So when combining functions, you need to look out for ranges and domains, but otherwise it's pretty simple to add, minus, subtract, or divide them. Just as a side note, if you're dividing them, let's say fx is x minus 3, gx is x minus 2. If we had a division, hx equals x minus 3, obviously the input can't be 2 because, well, it's on the denominator. So you also have to watch out if the operation creates a new hole in the continuity, which is called a discontinuity, but that's for advanced more advanced mathematics, like in calculus. So x can't be 2. This can be simplified into 1 minus 1 over x minus 2. And for the range, so if we have something like this, it creates a hyperbole, which in this case would, well, a general hyperbole. This actually is something like the graph of 1 over x. It creates a hole in the y and the x because of the hole here. In this case, this can't be 1 because 1 over x minus 2 can't be 0. Also, operations are not the only way we could combine functions. Let's say fx equals 2x minus 3, gx equals 1 over x. We could composite these functions, or rather these functions become composite. You can just call it combine the functions. So what does this notation mean? Let's just say this is hx. So first of all, we have fx in the input of gx. This is a composite function. It first x goes into f, and the result of f goes into g. It can be done with more than one variable, of course, but let's take these. So the output of fx is, in terms of x, 2x minus 3. And so we'll have g 2x minus 3. So the input is 2x minus 3, and the function is 1 over x. A good way to see this is this as a dummy variable. It's a substitute. So what we could do is just substitute this into this. I said that wrong. This is more of a substitute for this. Since the result of the input determines what gets put in the actual equation, so this gets substituted into this, which is 2x minus 3, and so the final hx would be 1 over 2x minus 3. Now, a few things. First off, g can't have an input of 0, and thus 2x minus 3 can't result in 0 because fx is going into gx, so x cannot be 1.5, which would result in fx being 0. Moreover, if moreover, the range of fx, which is what f can produce, and g, the domain of gx, what gx can intake, must have at least one value, because otherwise anything fx produces can't go into gx. Normally, you don't really have to think about this because most functions have pretty wide ranges and domains, but it's something to be careful of. Now, this has a hole in its range, as I talked about hyperbole, and I might talk about it later. But this can't be 0, so gx can't be. The range of gx is anything not 0. Moving on, does anyone have any questions before I do so? So inversing function. So we have the input to output, which we'll call fx for. Now, what if there was a function f minus 1x such that any output of fx goes back to its original input? In other words, could there be a function f negative 1x, which is the notation, equals x goes out, output goes in, inputs goes out. So let's see. First off, let's just give these, let's define fx. Let's see if fx matters. So f minus 1, 2x minus 3 equals x. Mind that x could be anything here. So x equals 1, x equals 0, x equals 57.2. They all have to fulfill this. So how do we solve this? Well, first off, if f turns input to output and f negative 1 turns output to input, then this must be equivalent to this. Since input because even though f minus 1 is the inverse of f is also the inverse of f negative 1. If you were to take it into terms of input and output, x goes into an output stage, and so this turns into output, input. So f minus 1 would go into a would be input, or to be more precise, it's what x would be. It's what f minus 1 x gives us a value such that f minus 1 x is x, since x is the original input. No, I'm explaining this one. F minus 1 x gives whatever whatever gives x from f. So x is essentially taken as an output. So when you put f negative 1 into f, it is x, showing that these two statements are equivalent. It also shows that these inverse functions are the inverse function and the functions are inverses of each other. And actually, this is easier to use than this. If I explained that wrong, feel free to ask me to explain it again. So f negative 1 x. So fx is 2x minus 3. So we have to find a function, an expression really, f negative 1 x, such that this is true. So what we can do is just take this as a variable y, or rather it can just stay as itself, variable f negative 1 x. And as such, solving for this variable in terms of x, we get that the inverse is x plus 3 over 2. So this worked out for linear equations. You can try it out other linear equations, but they pretty much all work. However, f equals x squared. So let's hypothetically take an inverse here. So f negative 1 x equals square root x after you square root everything, because this is f negative 1 x squared. However, let's say x is negative. Then, sorry, clearing my throat. Then this put into inverse would be imaginary non-real number. I'll talk about that more today, actually. So you see this inverse thing breaks down. Why is that? Also, if you look at it from the other side, it gets no better, since it produces the positive version of any negative input. So why is this? So let's look at x squared. It looks something like this, xy, and I won't, and a linear equation looks like this. So I talked about how an input can have multiple inputs trailing to it. This is true in this. Let's say 9, both negative 3 and 3 go to it. However, when we take an inverse of such a thing, input switch with output, input, output, output, this is not a function. Or rather, it can't be a function, since an input has multiple outputs. And so we get to what we call one-to-one graphs, which is like a linear equation. And each input has its own unique output. So any output here has a unique input and vice versa. On the other hand, these two inputs share two outputs, and thus it can't form an inverse. So a good measure of this would be if you had a graph to draw a horizontal line. If any horizontal line drawn like this, anywhere on the graph, if it travels through 2 points, it can't be inversed. Now, an interesting thing about x squared is square root x. So first of all, the domain of this is all non-negative numbers, and it fulfills the one-to-one basis. So it does have an inverse x squared. However, x squared does not have an inverse. The only reason x squared has an inverse here is because of square root x's domain issue. If we had a function in fx equals x squared where we arbitrarily, which means that we decided on our own that our inputs have to be at least 0, then this would have an inverse, because it would look like this. And as always, you should watch out for domains and range issues when you're looking at functions. So graphing functions. So how do we graph functions? So it's simple. We just set fx to y, or any expression of functions. So fx equals 2x minus 3. And I'll go to decimals for this actually. I'm using decimals because it's free. So let me draw a box of whatever's here so you can see what I'm drawing or writing really. So I'll draw a function. Also, the function itself doesn't matter. It's about the changes in functions. Not that actually. What am I writing? Okay, so we have our arbitrary function. It's squiggly. So let's call this function fx for so fx equals y produces this. However, what if I wanted to shift this function? What if I wanted to move up this function? Or really moving up the graph, I'm not really changing the function. So let's say moving to the right. So let's use hx for our modified function. So h1 equals f0. Similarly, h2 equals f1 since we're moving everything to the right. And so you can see that hx equals f x minus 1. I mean x plus 1. So if we wanted to shift the graph right, we would just have to type in this. Similarly, if we wanted to move left, x minus 1 over x minus 1. By the way, 1 is an arbitrary number. You can shift it right or left any distance. So y. Hold on a sec. Also note that while fx plus 1 equals, I didn't, whatever. This is arbitrary. hx no, I wrote it wrong. There we go. So h1 equals f0, meaning that fx is x plus 1. No. X plus 1. And regardless, I got it mixed up. X minus subtracting from the input moves it to the right, as you can see. That's because hx equals fx. Plus 1. And so to get excuse me for a second, I need to well, it's because of so hx minus 1 equal, regardless, is minus 1 would shift it to the left, but since it minus 1 is x negative, but it has to shift to the right to gain the same values it had. So it shifts to the right instead. So fx plus 1 adding the 1 shifts it right, as you can see. So if I draw a simpler function like x plus 1, I'll actually draw this. x plus 1 shifts it to the right, since it has to compensate for the added 1 to the right. X minus 1 goes to the right, since it has to compensate for the left. So adding to the input makes it go left. Subtracting to the output makes it go right. Does anyone have any questions on that? I messed it up initially, which is why you guys should check that your transformations actually work the way you want them to, which is what we're doing, by the way, transformations. Functions, basically output here, input into output. And inputs can't have multiple outputs, but outputs can share multiple inputs. This class is being recorded, so you can review more in detail later. But what about shifting up and down? So fx plus 1, well, let's take any x function. So let's say f0 plus 1. Well, know that and let's call this h and 0 for, because I'm inputting 0 right now. How does h change to f? Well, the y here, let's pretend this is the original, and input 0, f0, h0 equals f0 plus 1. And so everything h0 has is 1 y unit above f. Similarly, if this was minus, it would be 1 below. So let me draw it out. X squared original fx. Let's call this gx. It's 1 below. Y equals x squared plus 1. It's 1 above. So we've done additive transformations. How about we do something like this? So y equals fx. What if I times the 2 in there? By the way, you can simplify these functions with expression in them, but by just using this, but g being the expression in it. So g would be 2x. You can get it from there. So what does this do? So let's take f1, and this would be 1. So if this were hx, let's say 0.5 f1. So it would be something like this. It's squished. So if I insert 2x there, we'll substitute 2x more accurately. No, it squishes it a bit. If we times 0.5, it widens it. So multiplier above 1 squishes any multiplier below 0, below 1 shifts outwards. And by the way, only on the x-axis, which is x direction, I should say, which is horizontally. If we wanted to stretch it vertically, well, let's try it. Y equals 2fx. So, and let's also take f 0.5 fx. So if we had a point 1 on fx, the same point would be f2 f1x. So any y here is doubled. So it would be something like maybe x was a bad example for this, but if we had 2x minus 3, and I'll put everything. So this is the first, this is squishing it to the x, and this is expanding. Now let's do it by the y. No. So this is the original, it expands. It actually expands. No, this is the original. So it expands to the y. So anything here is doubled on this line. Original is blue line. And if we squish it, which is by the same principles as the horizontally, so times it by 0.5, as you can see, it goes by the same except x is half. Now you see that all these 3 changed by the x go through the same x-intercept and y-intercept, which is, I mean, by the y-intercept, I mean the one squished or expanded vertically. So that's something interesting to note. And you can actually compress or expand a function while adding something to it. So like I can raise that by 3 while it's squished. Okay, so that's it for transformations. Does anyone have any questions? A reminder if it wasn't clear, but minus f minus x minus 1 shifts it to the right, fx plus 1 shifts it to the left. It was a bit unclear before. But let's go on to imaginary numbers. So imaginary numbers, what are they? So I've talked about this not actually giving an actual answer since there is no actual answer. But this is why imaginary numbers come in. So I, by definition, is square root -1, but I isn't actually a real number. That's why it's called imaginary. It doesn't actually exist. So let's take square root 3. So radicals times each other. Square root 2 isn't 4, but square root 4 is 2. So you can multiply radicals together. So this is real because it's just radical 3. This is I. So square root 3i. Now you can multiply I, 5i plus 3. Or you can multiply I. So what happens when you multiply I? So what is I times I, or I squared? So since the basis of I is -1, square root -1, then I squared must be -1. Now there isn't actually any real basis for an I existing like this, but it's true by definition of I. Similarly, I3 is -1 times I times I squared, which is -1, so -I. I4 is -1 squared, which is 1. Now, while I4 equals 1, it's important to note that I does not equal 1 to the 4th root. Now, but it is important to note that I5 is I, so it cycles. I5 equals I squared equals I6, I1 equals I9, etc. It cycles by 4. Now, why do we have imaginary numbers? So the main point of imaginary numbers is so that we can write complex numbers. Why complex numbers? Because later on you will learn how to write 2 dimensions in one complex number. And what is a complex number? A complex number is this. It's a real part plus an imaginary part, where a and b are real. So 5 plus 3i is complex. 4 minus 2i is complex. -I by technicality is also complex, but 5 is just real. So b is non-zero here, and a and b are real. So a few things we have to talk about complex numbers. First off, adding them. So let's say we had, so first off, we can't add a real number and I together. They are fundamentally different. But what we can do is add imaginary numbers with imaginary numbers and real numbers with real numbers. So this would turn out to be a plus c plus b plus di. So if we had 3 plus 4i plus 4 plus 5i, this would add up to 7 plus 9i. Now, what if we wanted to multiply them? So, well, we can't just expand it out, and we can't just multiply it, since, again, imaginary numbers are different from real numbers. However, we can distribute them out and expand that way. So 3 times 5, 3 times 7i, 4i times 5, 4i times 7i. We can actually do what we did in binomial or polynomial multiplication and just set up a multiplication setup. And 4i times 7i is negative 28, so negative 13 plus 41i. Another thing I should talk about is complex numbers in relation to quadratics. So I've talked about this being the quadratic formula and giving you the solutions to a quadratic. However, let's say x squared plus x plus 40. I'm choosing 40 here because I know it's going to be complex. What I mean by that is, so this, if you put it out here, this becomes negative 159. I've said before that this is real. However, it is imaginary. Put out negative and then put an I. Although you can put the negative out, you need to keep the radical inside. So the solutions to this would be negative 1 plus minus square root 159i divided by 2, which you can actually write as roots like this, but it's not very nice to write these. Also, an important note on the subject of this, but let's take two similar complex numbers in that a plus bi, a minus bi. And this is similar to this, how this works. Now, as I've talked about before, these are the properties, I should say, of roots in a quadratic. However, b is real and c is real, while r and s are not real. So this is because of a conjugate. If you multiply this out, you get a squared plus b squared. It's a real number. Similarly, if you add them, you would get 2a. So as you can see, conjugates are very useful for turning something that might be complex into real, possibly. So like 1 plus I, we can't just leave this imaginary number on the bottom. It doesn't make sense. What is 1 over 1 plus I really? So let's do what we did with radicals and times it by 1 minus I, its conjugate. So this becomes 1, 2, and 1 minus I, and it becomes the complex number formula, or a plus bi.